The objective of this video is to review Maxwell's equations and their application to electric machinery. We're going to establish field equation definitions and the nomenclature that we'll be using throughout the course. This lecture is going to cover all four equations and the way that we think about them when we apply them to electric machine analysis. So let's get started. Maxwell's first equation is known as Gauss's law. It states that the divergence of an electric field is equal to the charge density divided by epsilon naught. This equation is actually not going to be used in this class. This does come up in electric machines when you talk about insulation issues and dielectric strength. However, in this class we're going to be focusing on the magnetic behavior and the electric circuit behavior. Although, since we've written this equation out, let's take some time and look at the quantities that are shown inside it. First, we've got our electric field, E. And our electric field is in units of volts per meter. In practical materials that we'll be using in this class, we can relate our electric field to our current density, J, through the material conductivity. And conductivity is a material property. Mostly we'll be talking about the conductivity of copper for our coils. So J, again, is our current density, and it's in units of amps per millimeter squared. Or sometimes we'll specify it in units of amps per meter squared. We can integrate J over a surface to determine the total current flowing through a conductor. So if you have some surface that you've got a current density flowing within. So if you excuse my drawing skills here, this is supposed to represent some kind of conductor. Within a cross-section of that conductor, we have a current that is traveling along it axially. We can integrate that over the surface, S, and that gives us the total current through the conductor. Alright, let's move on to equations that are actually going to be used in this class. And that is Maxwell's equations 2 through 4. So the second equation states that the divergence of a magnetic field is equal to 0. This simply means that we have no magnetic monopoles. So while we have point charge for electric fields, we do not have point charge for magnetic fields. More useful, we can write this in integral form to say that the integral of our magnetic field over a closed surface has got to be equal to 0. What does this mean? Well, suppose that we have some structure. I'm going to draw this as a cube. What this is saying is that if we have magnetic field entering a surface of our cube, it must exit another surface. So I'm drawing with these arrows flux paths of field that are coming into our cube, and you'll see that they're exiting on different surfaces, but the point is that they all must exit. So if we were to evaluate the integral of the magnetic field over every surface of the cube and sum it up, we'd find that it's equal to 0. Alright, so let's now talk about magnetic fields. We use B to represent a magnetic field, and we also call magnetic fields flux density. And magnetic fields in this class will have the units of Tesla. So that was Maxwell's second equation. It does not have a name. Maxwell's third equation is Faraday's law. Faraday's law states that the curl of our electric field is equal to the negative time derivative of our magnetic field. This equation is more useful if we put it into integral form. And working on the right side of this equation, we can integrate our flux density over a surface to come up with a flux. Let's talk about what that means. Earlier, we had described how current density can be integrated to become a total current. Well, magnetic field is oftentimes referred to as a flux density because we can integrate it to talk about a quantity that we refer to as flux, magnetic field flux. So you can think about B similar to how you think about J. And the integral of B over a surface is the flux that's passing through that surface. And if we assume that our magnetic field is evenly distributed across the surface, it comes outside the integral, and we can just simply write that B times our area is equal to flux. So depending on the type of machine geometry that we're studying, we may be able to make this assumption, or we may not. And phi is our magnetic flux. It is in units of Webers, where 1 Weber is equal to 1 Tesla meter squared, because we've integrated Tesla over a surface. So flux is analogous to current, and flux density is analogous to current density. All right, let's go back to this equation that we've been working on over here. We can now use vector calculus identities to rewrite this in terms of a line integral. The integral of the electric field over a closed path is equivalent to the integral of the curl of an electric field over a surface, where this path now surrounds that surface. And that's going to be equal to the right-hand side, which is negative d phi dt. And this quantity is referred to in the literature as our EMF, and in our textbook it is typically denoted by a lowercase e. So EMF stands for electromotive force. This is a voltage that pushes charge around a circuit, that causes a current to flow if there is a conductive path. So epsilon, or lowercase e, is our electromotive force. And it has units of volts. So let's talk a little bit about what this means. Suppose that we have a coil that is wrapped around like a solenoid. And say that it's wrapped around n times, that we can say it has n turns. Well, if we have a magnetic field that flows through this solenoid, so we have a magnetic field that is going through this coil that has n turns, we can talk about a flux that links each turn of the coil. So again, phi is equal to the integral of b dot ds. We can talk about a voltage that gets induced in this coil. So as this flux increases or decreases, we have this d phi dt term here. And suppose that b is increasing, so that our phi is increasing. This means that we're going to experience a voltage across the terminals of this coil. And the voltage is going to be such that if we were to attach a resistor here, we would get a current that would flow in a direction so as to oppose the change of field. Our EMF is going to cause a current to flow that's going to create a magnetic field in the opposite direction as the changes in the current field. So if this field is increasing, we're going to induce a current that is going to create a counter field that will cancel out part of that increase. And you can refresh yourself of the right-hand rule for the direction and the sign of this. Our book gives you some reference to this. You can see that the direction of current, in order to create a field that will oppose the increase of our blue flux lines, is as I'm labeling right now with these black arrows. In order to make this happen, we're going to require a voltage to appear across the terminals of this coil of value E. And so if we have a positive voltage on the top terminal and negative voltage on the bottom terminal, this will cause a current to flow out of this terminal into the resistor and take the path that I've indicated with the arrows. The back EMF that links a single turn of this coil will label as E1, and that's going to be equal to a negative d phi dt. But the back EMF that is exhibited at the terminals of this entire coil of n turns is going to be n times d phi dt. Now, if we're being precise about this, we'll notice that the surface area of each of the coils varies. Our later coils have a smaller surface area and then presumably link less flux. So in this class, we'll denote this, or we'll account for this, by introducing something called a winding factor, Kw. So in this case, Kw is some quantity that's less than 1 that accounts for the fact that not all coils link the same amount of flux. And we'll get into defining what we mean exactly with a winding factor later in the course, but I want to introduce the concept now that the winding factor is a means of accounting for a different amount of flux linking each turn of a coil, or if you have many coils in series, a different amount of flux linking each of the coils when you connect them in series. And finally, we can denote all of this by saying that this quantity is equal to the time-varying flux linkage of our entire coil, where psi is our flux linkage in units of Weber turns. And flux linkage is different from flux because flux talks about the flux linking a single turn of a coil, where flux linkage talks about the flux that links the entire coil when all turns are accounted for. All right, let's now talk about Maxwell's fourth equation, which is known as Ampere's law. And as I've written it right now, this is actually the Ampere-Maxwell law. Maxwell added this term right here, which is known as displacement currents, or the displacement current term. And in our class, we're going to neglect this term. We're going to assume that it is negligible compared to the rest of this equation. And this is a fair assumption for low-frequency devices like motors. You have to worry about the displacement current term when you're operating at very high frequencies, such as radio frequencies. At this point, it is convenient to define a new field quantity called the H field, or the magnetic field intensity. And the H field has units of amps per meter. So we do this purely as a mathematical convenience. It's a trick that we are playing. The H field is not a physical quantity. The physical quantity in a magnetic system is the magnetic field, or the flux density. But as you'll see throughout this course, the H field makes things much more convenient for analysis. And it's a very convenient tool for calculating the field quantities throughout our motor cross-section. And you'll see that we've related it to our magnetic field by the quantity mu, where mu is our permeability. And mu is the product of mu naught, which is a physics constant, or the permeability of free space. And it has a value of 4 pi times 10 to the negative 7 newtons per amp squared, or henries per meter squared per meter. Mu r is called our relative permeability. It is a dimensionless scaling factor, and it's a material property. In electric machines, we treat this as a material property that you'll actually have specified for you from your motor material manufacturer, from your steel manufacturer, in the form of a BH curve that will be provided to you. We'll talk about that more at the end of the lecture. And we'll just note that mu r is equal to 1 for a vacuum or air. So basically, in the air gap of our motors, we treat mu r as being 1. And in our steel, we treat it as having a value that we extract from the data sheet for the steel that we are using. So this entire quantity, mu, is the permeability of our material. When you're working in magnetic materials, when you're working in ferrous materials, it is a function of the magnetic field. Mu naught is a physics constant, but mu r, our relative permeability, varies as a function of our magnetic field, or a function of our flux density. That is to say, it saturates. And again, we'll come back to that at the end of this video. Ampere's law is also most useful to us in this class when it's in its integral form. And now that we defined our H field, we can rewrite it in terms of our H field as the curl of H is just equal to J. And then using the same tricks we did before to put this in integral form, we can say that the integral of the curl of H over a surface is equal to the integral of our current density over that surface, which is just equal to the total current flowing through that surface. So I'm labeling this as I enclosed for reasons that will become apparent in a minute. I just want to point out quickly that the current through that surface can be a continuous current density like we talked about up here, or it could be a set of discrete conductors, which I'm going to give you an example in a second. Okay, so working on the left side of this equation, we can use the same vector calculus identity that we used earlier to put this in terms of a line integral, saying that the line integral of h over a closed path that surrounds that surface is equal to the total current flowing through that surface, and this quantity is the MMF of our field on that surface. So this stands for magnetomotive force. We talked about electromotive force earlier. Now we have defined the magnetomotive force, or MMF, and this has units of amps. So let's depict pictorially what's going on here. Suppose that we have some core of ferrous material, of steel, that looks like this. The shaded gray region is steel, and inside it is it's hollow inside, and we've placed conductors in there that are carrying a current. So I've drawn 4 conductors, but let's just generally assume that we have in here, we have N conductors that each have a current of I. And so when we draw conductors carrying current, we use a circle with a dot in the center to represent a conductor that's carrying current coming out of the page. And this is the same for fields too. We can draw this for fields as a circle with a dot in the center, and that means that you have an arrow coming at you, so it's coming out of the page. The arrowhead looks like a dot. And if we were to draw a circle with a cross in the center, that would indicate a conductor with current going into the page. And so the cross is supposed to look like the feathers at the end of an arrow. So the dot looks like the arrowhead is coming at you, the cross looks like the feathers at the end of the arrow, so the arrow is going away from you, and that is a conductor carrying current going into the page. So if we were to evaluate the line integral of h dot dl along this path that I am dashing right now, it's going to be equal to the total current that's enclosed, which is, again, the integral of j dot ds. And so in this case, that's equal to Ni. That's equal to N turns times I current. That's the total current that's enclosed in that surface, and that's going to be equal to our magnetomotive force, Fm. So we can see some analogies here between our electromotive force, which was N times d phi dt, and our magnetomotive force, which is now N times I, the current in each coil. We'll see in Chapter 2 and later in this class that the winding factor also applies to the MMF created by current. But in this simple example, it's difficult to show. Next, let's define the Lorentz force law. So we've listed out Maxwell's equations, and now we have a couple of housekeeping items to wrap this up. And the first of those housekeeping items is the Lorentz force law. And again, I expect that this is review for you, though we may be presenting the material in a different manner than you're used to from your fields courses. So the Lorentz force law, we'll write this as a differential force. This is a force that is acting on a differential amount of charge. So our differential charge is dq, and the force is dq times the quantity of our electric field plus the velocity of the charge, the cross product of the velocity of the charge with our magnetic field. So if we work on this equation a little bit, we can manipulate it into all types of forms, which will be used throughout this course. But I want to draw your attention particularly to the following form. We rewrote our velocity term as being our velocity times our differential charge as being the quantity dq by dt times the differential length, or the direction that our velocity is going over one differential unit of time. And dq dt is simply equal to a current. In this form, we will especially use this later term, which ends up being the principle, used to calculate the principle of torque in most electric machines. So that is the Lorentz force law. And the second of the two housekeeping items is to come back to this topic of magnetic saturation and magnetic permeability. So what your steel manufacturer will provide you with is called a BH curve, and this is simply a plot of the magnetic field that is created in the steel as a function of the H field that you apply to it. So we apply a certain H field by flowing a current, and we observe how much magnetic field we get. And if you plot this, you'll see a characteristic that will look something like this, where this slope right here is our permeability mu. Because if you recall, we had defined H such that mu times H is equal to B. And remember that mu is equal to mu r times mu naught, where mu naught again is a constant, but mu r is a function of H, or actually B and H, B or H. So you'll notice that this relationship has a region where it is approximately linear, and so we say that from about here and lower values of H, we are in a linear region, and then out here we are saturated. And so we talk about the saturation quantity of our steel. That's the maximum flux that it is able to carry before it starts to look like air, in which case mu r approaches 1. The point that it becomes saturated depends on the type of steel. This can be somewhere in the range of 1.5 Tesla to approximately 2 Tesla. Higher saturation levels are possible with iron cobalt alloys. For traditional silicon steel, you're down around 1.5, 1.75 Tesla. So that wraps up this video. Again, the point of this video was to review Maxwell's equations and talk about how we're going to apply them to electric machinery, and to establish field equation definitions in our nomenclature. So we specifically talked about Gauss's law, and in fact that we're not going to be using Gauss's law much in this class, but we use it to define our electric field. We talked about conductivity of a material, current density. We talked about how magnetic fields have no monopoles, and so we can express the surface integral of the fields across all surfaces. We can sum up the fluxes through all surfaces of a closed body to show that there's no net flux. There can be no flux lines originating within a body. And we defined our magnetic field, the units of our magnetic field. We discussed Faraday's law and how we can use it to calculate electromotive force, or EMF. We defined magnetic flux. And finally, we went through Ampere's law and used it to define MMF and introduced the concept of permeability. And finally, we had our two housekeeping items, which were to review the Lorentz force law and the magnetic permeability and saturation characteristics of steel.